The complex number system are the numbers that include the real numbers, which we have talked about in the past. Remember, the real numbers are 3, 8, 0.3, 0.385, that doesn't repeat, as well as the imaginary numbers. And our focus today is going to be on this imaginary number system. What are imaginary numbers and where do they come from and why do we use them? Well, an imaginary number comes from the idea of a radical, but the radical of a negative number. If we take the square root of a negative 1, we don't have a number times itself that'll give us negative 1. So what we say is that we can take this negative 1 out and be able to simplify this as simply the letter I. And this would be our imaginary number. We can simplify, as an example 1, any radical that has a negative in it now. For example, the square root of negative 18. If I take the square root of negative 18, I can break this into negative 1 times 9 times 2. Square root of a negative, again, is I. So this becomes 3I, because the square root of 9 is 3, radical 2. And this would be an example of an imaginary number. In example 2, let's take negative 4 times the square root of a negative 72. Well, 72 we can break up. We have negative 1 for our negative. 72 is 36 times 2. Square root of 36 we know as 6. And negative 1 is I. So we're going to multiply that 6I to negative 4 and get our final answer of negative 24I radical 2. We can include numbers in the real number system with the numbers in the imaginary number system to get a complex number. So an example would be 4 plus the square root of negative 32. To simplify this, 4 we don't do anything with, but negative 32 we can break up into negative 1 times 16 times 2. The square root of 16 is 4, so it can go out, and negative 1 can go out as an I. So our final answer would be 4 plus 4I radical 2. Notice we have our real part and we have our imaginary part. Together it makes the complex. So here's our real, here's our imaginary. Together it's a complex number within a complex number system. We normally like to have all of our answers in the real plus the imaginary or minus the imaginary. The question then becomes is, how do we graph, or what does it look like? Where does it come from, these imaginary numbers? Well, let's take an example, 4, and let's look at the graph in the complex number system of 3 plus 2I. We're going to start with a graph that we've seen in the past. Normally we call this the x-axis and this the y-axis. Now we're going to call this the real number line, or the real axis, and this the imaginary axis. And we're going to graph this just like we would graph a number or a coordinate on the real number system. The point in this case is going to be the real number followed by the coefficient of the imaginary number. So we have 3, 2. So we're coming over 3 and we're coming up 2. And that would be the graph of this point, 3 plus 2i. What we also like to do with these numbers is to take the absolute value of them. To take the absolute value of 3 plus 2i is simply asking us how far away is the point 3 plus 2i away from the origin. In order to find that, we use the distance formula. But if we think about this as a point, because we're coming over 3 and up 2, we can also think about it as just a point for 3, 2. To find the distance, we take the square root of x sub 2 minus x sub 1, or x values squared, and we add on the distance, or the difference, of the y values squared. If you remember this from geometry, we have the distance formula. So our example here, well, if we treat the origin as x1, we're really simply looking at x2 squared plus y2 squared, or the real number squared plus the imaginary number squared. So here we have the square root of 3 squared plus 2 squared. Simplifying that, we have the square root of 9 plus 4, which is the square root of 13. So the absolute value of 3 plus 2i is radical 13. If we could simplify this, we would go ahead and simplify it. Otherwise, we leave it as radical 13. In example 5, let's take the absolute value of 6 minus 4i. Again, we could look at the graph of this. We would be graphing the point 6, negative 4. So looking at the graph, we would come over 6 and come down 4. So this would be our point. To take the absolute value, we're looking for this distance. So our absolute value, since this is the point 0, 0, we can simply take the real number, square it, and add on to it the imaginary number squared. Notice we have a negative 4 squared. If you forget the negative, it doesn't matter a whole lot, because a negative times a negative gives you the positive. So we're looking at 36 plus 16. Simplifying 36 plus 16 gives us 52. So what we have to look for is a perfect square that goes into 52, if there is one. Well, luckily enough, 4 times 13 gives us 52. So our 4 can come out as a 2, so we end up with 2 radical 13. And there's our final answer. For example 6, what I'd like to do is talk about the additive inverse. If you remember, the additive inverse is simply what undoes a function, or what undoes that operation. If we look at a complex number, 2 plus 7i, to find the additive inverse, we're simply going to take the negative of the complex number, 2 plus 7i. So take the opposite of the complex number. We can simplify this by multiplying the negative through, so we end up with negative 2 minus 7i. And that's our final answer excuse me, for the additive inverse. one more example, just for good measure. Let's say we have 3 minus 9i. To find the additive inverse, we're going to take the negative of 3 minus 9i, multiply the negative through, distributing, we end up with negative 3 plus 9i. And there's our final answer. So to recap what we've looked at today, we talked about the complex number system being the real and imaginary numbers, that I is the square root of negative 1. We can simplify now radicals with a negative under the radical, or a negative radican. We wrote numbers with the real numbers and imaginary numbers, remembering that the real number comes first, then the imaginary. We've talked about how to graph in the complex number system, that we have the imaginary axis, or the y-axis, and the real number as being the x-axis. And then we looked at the absolute value by looking at the distance our point was from the origin, or just simply taking the real number squared plus the complex number squared, taking the square root of that. And we also looked at the additive inverse by simply taking the negative of the complex number. And that concludes our complex number system.